moving on. Indicial equation. Example, 10 to the power of x is equal to 36. If, as in the example, the equation involves the power index, where x is the unknown, is either the base or the index, we have an indicial equation. So another example might be so where you've got the variable is involved in as either the index or the base, then you've got an indicial equation. You can solve an indicial equation by using logarithms, usually logarithms to the base 10 or common logarithms. The logarithm to the base 10 of a number is the power to which I have to raise 10 to get that number. So it's, what do I have to raise 10 to so that it equals 36? Okay, the log button on your calculator finds the log to the base 10 of a number. So calculator's out now. What is the log? And we assume 10, so log of 1000, according to your calculator. 3. And 10 to the power of 3 equals 1000. Yep, so when we've got an index of a base of 10, the power is the log. Yeah, so if we had 10 to the 5, which is equal to 10 and 5 noughts, yeah, five is the log of that number, isn't it? Yeah. Log to the base 10 and 98 to 4 significant figures is 1.991, and then if you do 10 to the power 1.991, you won't get it exactly because you rounded the 1.991. Comes out as 90 something, 97.94. Yeah, so 94899. That's 97 point what? To 4 significant figures. 97.95. Yeah. So log and 10 to the x, as we talked about on the other page when we talked about opposites, mathematical opposites of each other. So if logarithms are powers, effectively, then we can apply the laws of indices but write them as the laws of logarithms. So what we can do here is say that the log of a times b, in brackets, is equal to the log of a plus the log of b. Back in my old days at school, one way of multiplying two big numbers together was to find the log of them, add the two logs together, and then find the anti-log or the inverse log of the result. If we got two numbers a and b that we want to multiply together, We can find the log of each of them, add them together to get the result, and then take the anti-log of that result, and we've multiplied the two numbers together. That's what that law is effectively saying. The log of A over B is equal to the log of A minus the log of B. The log of A to the n is equal to n log of A. And that one's going to come useful in a minute when we go to solve some indicial equations. Remembering that the log of 1 is 0, whereas 10 to the 0 equals x to the 0 equals 1. Yep. So there are laws of logarithms that we may well be able to apply when we're trying to solve problems involving indicial equations. For example, solve 2x, 2 to the power of x equals 3. Correct to 4 significant figures. Okay, go through the method here. So, if we take the log to the base 10 of both sides, so that's the operation I'm going to do. I'm going to go log of 2 to the x is equal to log 3. Yeah? Now look in your laws of logarithms and see if you can find another way to write that. X log 2, yeah? So we can write this side, apply that law, log of A to the n is equal to n log A. That's what we're applying. So we end up with, as someone rightly said, x times the log of 2 is equal to log of 3. What can we do now, bearing in mind that what x is what we want to find? Sorry? Well, you could do, but what else could you do first? Remember, if we want to find x, we've got to get it on its own. What's between that x and that log 2? Yeah, we've got to multiply in there, so we divide through by the log of 2. Remember, the log of 2 is just a number. And at this stage, if you leave it as the log of 2, you haven't done any rounding and you haven't caused any issues with missing numbers off. So, divide by log 2. Effectively, those two cancel each other out because they're just numbers. We're left with x is equal to the log of 3 divided by the log of 2. Log and log don't cancel out to leave 2 over 3. And then you can plug that in your calculator and get the answer to the correct of 4 significant figures that are asked for in the question, which is, and I suggest you use your fraction button. What is it? 1.585 to 4 significant figures. Yeah. So initially we've applied that law, log of a to the n is equal to n log a, to get x out from inside the log function. Yeah, and then normal rules of rearranging applied to get x on its own. All reasonably happy with that one. Yeah, and those laws of logarithms, another set of rules, maybe to put in some place in your folder right near the front where they're really handy and you can get at them quickly if you think you need them. Further examples on the laws of logarithms. So the top one, what are we going to do? In fact, have a go at those two. I know the second one's probably a little bit more tricky. I'll have a go at them, 5 minutes, and then we'll go through them. Right, the first one, 3 to the power of x, sorry, is equal to 112. First thing to do is okay, yeah, so you're going to do that all in one go. So what you've effectively done is said log of 3x, 3 to the x is equal to log of 112, and then applied the law of the logarithm. So that's log of both sides. And then you're doing log of a to the x is equal to x log of a. So you're going x log of 3 is equal to log of 112. And that's a lot of what we're doing when we're rearranging mathematical expressions and equations, is often just trying to find a different way to write something so it'll allow us to eliminate something else or move something else, whether that be factorising, whether that be taking the inverse, writing things with the indices, getting rid of fractions, all that type of thing. Is how can we change this, write it in a slightly different way that will help us solve the problem. And then what we can do, divide by log 3, so we end up with x is equal to log of 112 over log of 3, and that is, for 4 significant figures, 4.295. Did you all get that result? Anyone got anything different? Shout. It is really important if you got something different, because you've gone slightly the wrong way, because that's important we go through and I help clear up any kind of misunderstandings. So do shout, because there might be others in the room as well, okay? And I want you to be as good at the maths as you possibly can. So, right, who's going to have a go at going through this one for us? What do we do? Take it step by step. Definitely go one stage at a time here. So what you got to do first? Let's do log of both sides first. If you take the log of both sides, we end up with log of 4 x to the power of x plus 2 is equal to log of 13.8. Yep, so you've done that, and then you're applying log of ax is equal to x log a. Just let me adjust that. That's a to the power of x. So you're applying that. Yeah, so what do I write down? What do you want me to write here if I'm applying that? X plus 2. Yeah, let's bracket that. Important, right? Log of 4. Next. Mm-hmm. Yep. Oh, okay, yeah. Which that works. Yeah. Yep. All right. Yeah, you'll get the same answer if you here write. If you go at this state, are you saying if where I subtract -2, subtract 2 from both sides? No, it's got to be all of that, take away the 2. So you'd write it like this: x is equal to log 13.8 over log of 4 minus 2. Further up, go on. You can't take the 2 away there. You can't do that because that's it's multiplied, all that's in that brackets is multiplied by the log of 4. You can multiply those brackets out first, and in some cases you might have to do that to end up with x log of 4 plus 2 log of 4. Right? But you didn't have to do that in this case. But no, you can't subtract the 2 there because that's inside the brackets. When you do this moving around, you're almost doing reverse of BIDMAS because you have to get rid of the multiplication first and then add or subtract. Yeah. Just depends. We have to get rid of what's outside the brackets first, or we multiply the brackets out. So have a go at the one on the next page that's got an index on both sides. So let's go through this. Let's find out where things are going wrong. So if I get Dom to take me through list what they've done, that sounds like they might be similar. Tell me where it's different to what you've done. Right? So Dom, what do you do first? Log both sides. So we write that we got the log of 2 to the x plus 1 is equal to the log of 3 to the 2x minus 5. Then using that rule, what do I write? Yeah. Okay, so far, so good. What do you do next? Okay. Divide both sides by log 2. So let's go down this road. What I got then, what you end up with is x plus 1, yeah, is equal to 2x minus 5 in brackets times a log of 3 all over the log of 2. Yeah? Your next bit. How does that differ from what you've done? So you went along the route of multiplying out the brackets them logs. Okay, we'll carry on with this direction for a minute. Done. So yeah, okay, so you got x plus 1 over 2x minus 5 is equal to the log of 3 over the log of 2. Yep. Yep. Go on. No, you can't. What you have. That's where you're. What you are you trying to tell me that is equivalent to half of all of x plus 1 over x plus 5? Is that what you're saying? No. Well, it isn't anyway. Yeah. What you have to remember is it is all of that divided by all of that. Yeah. So you're when as soon as you moved that across, that log across there, and ended up with the two x's kind of separated and in their own brackets, was where you went wrong with that problem. Yeah. Because you can't solve that that way, because like x plus 1 all divided by 2x minus 5, so you can't cancel, you can't get rid of the numbers to get the x's on their own using that method. Alright, so I'm going to keep that page. Put a big cross there. That one's wrong, yeah, but it's a lesson learned, so that's why I'm going to keep it. Clone the page. Everything is right up to there. Alright? I keep forgetting your name for some unknown reason. Jake. Right, Jake. So you said something about multiplying 8 brackets. So tell me what to write then, Jake. I'll just put multiply brackets there, alright? Log 2. Why is it log 2 squared? Remember, let's just go back a step. Log 2 is a number, right? If you push log of 2 on the calculator, what do you get? 1.3, so 0.3, right? So log 2 is 0.3. If I wrote 0.3 times x plus 1. What would you tell me it is when I multiply the brackets out? So I've got 0.3 x plus 1. What would you tell me I got? 0.3x plus 0.3 times 1 is 0.3. Alright? So, knowing that log 2 is just a number, how do we multiply out them brackets? X log 2, x times the log of 2, that's our x times 0.3, yeah, plus the log of 2, yeah, equals, now apply the same rules to the other side. Everything in the brackets, remember log 3 is just a number. Times log 3 minus 5 log 3. So log 3 is not 3 letters than the number 3, it is, the whole thing is a number. And we can move the whole log term in one go. Nope. But good try, Lewis. What did you do? Is it building on what we've done here so far then?
No, I've done the whole,
yeah. So bearing in mind the overall aim is to get x on its own, what we do next? Go one step at a time as well. Yeah, subtract log 2. Subtract log 2. So you're going to end up on this side with yeah, agree with that. Next. If you do that, okay, we've still got an x term on this side at the moment, and that's got to have a log with it, 3. Sorry, that's got to have a number in there. I missed out. Yeah. How is this, we want all the x terms over there, don't we? How is this term with x in it attached to the rest of it? What sign is in front of here? Plus, yeah? So how do we get it the other side? We subtract it, yeah? So we are going to subtract 2x log 3 from both sides. That'll leave us with x log of 2 minus 2x log 3 is equal to minus 5 log 3 minus log 2. Now what can we do? Factorise the left-hand side. Good idea. Which factor do we want to pull out? Which one would it be handy we pulled out? So we're going to factorise it. We're going to put a bracket on this side. Bring x outside. Log 2. And just ask yourself, if we multiplied out those brackets, would we get back to that? We'd go x times log 2, gives us that. We'd go x times minus 2 log 3, we'd end up with that. And that is equal to minus 5 log 3 minus the log of 2. Now what can we do? Yeah, all of that, these two things are just numbers, one subtracted from the other, inside a bracket, the result of which is just a number. We can move the whole thing in one go. So you can divide by bracket term. So we can write x is equal to minus 5 log 3 minus the log of 2, all divided by log 2 minus 2 log 3. Now that's a job for your fraction button on your calculator now. Nope. Have I written it out right? Just make sure. You've used your fraction button, Lewis? Yeah, you have, yeah. No, they don't cancel. .11, yeah. 3 significant figures. So to check that, we'd need to do two to the power of 4.11 plus 1 equals, and 3 to the power of 2 times 4.11 plus 1. Sorry, for minus 5. Two x minus 5. So 2 times 4.11 minus 5. If you do each of those, if you're right, they should come out more or less the same. We're rounded, remember. So we're putting that into both halves of the original equation. We should end up with the same number. So that's plugging the result for x into the two sides of the original expression, the original indicial equation, and checking that they equal each other. It's a way to check that you've got the right answer. Okay? Now, in your notes, there are, oh hang on, one more to have a go at. Solve the equation x to the power of 3.2 is equal to 41.15. So here, x is the base, not the indices, not the index. Have a go at that one. So what we've got this time is x to the 3.2 is equal to 41.15. What are we going to do to it? Take the root of x here. Oh, I see. Yeah. Okay.
The other side.
You take the 3.23,
Yeah.
41.15. Okay. That's actually, you're doing what you're doing is that and saying they cancel each other out. Yeah. And the answer is the 3.23 to 41.5. Okay. The intention was that you apply the laws of logarithms. So you take a log of x to the 3.2 as equal to a log of 41.15. Yep. We apply 3.2 log of x is equal to a log 41.15. Yep. So the log of x is equal to log of 41.15 over 3.2. And what's the inverse of log function? So everything we've done there, but we're going to do 10 to the x, both sides. So that would make this side x is equal to 10 to the power of log 41.15 over 3.2. 10 to the power of all that. Give you the answer. Other bigger problems you might not be able to do that way. That's all due respect to you. 3.195, yeah. Just going to write that out a little bit neater, I think, for the benefit of the x is equal to 10 to the power of log 41.15 all over 3.2, and that equals 3.195. Yep, 2, 4 significant figures. Okay, so well done. That just goes to show there are sometimes other ways to do things. but dependent upon the nature of the problem, that way may or may not work. Alright? Okay, in your notes on that following page, there's some further practice solving equations that we done first. Then there is further practice rearranging formulae, and there are some harder worked examples and exercises in chapter 10 of the Bird book. You cannot have too much practice at these techniques. Okay, and then finally there's some further practice on indicial equations. Again, there are worked examples to help with them in your Bird book, chapter 13. Okay, I do encourage you, like Jack did during the week, is email me about something I have a specific problem with, and that's why I put the double bracketed term example in the drill up at the beginning of the lesson. I mean, if you all give me a different problem you're struggling with, I'm going to struggle to cover it all, but I'll pick some kind of key bits out of it and see if we can slot something in for the next session. Okay, one last thing I've done is I've had a look ahead, and I'd like you to jot down, you might get time to look ahead at what we're going to do next week, which is solving simultaneous equations and solving quadratic equations by the formula method, eliminating the variables, and factorizing methods. So it's solving simultaneous and quadratic equations. Okay, so the rest of our time, the remaining half hour this week, is have a go at the practice questions. If you get to a stage where you're doing one set fairly easily, move on. Try and have a go at least some of each of the 3 sets of examples I've given you.